Assalamualaikum and welcome back. Today we're going to continue our stiffness metric method for frame. For a recap, for truss, at each node we're going to consider horizontal and vertical displacement. This one for truss. And then for beam, at each node we're going to have vertical displacement plus the rotation, that for beam. And now for frame, at each node we need to consider horizontal displacement, vertical displacement and rotational. That means your matrix for each member gonna get bigger. Alright, now let's do for the first example. Here, problem number 1. We need to determine loading at joint of the member frame as shown, and the profile as given here, E, I and A. First of all, at each node for frame, we're gonna consider 3 types of displacement, which is horizontal, vertical and rotational. So as usual, we know our global direction, X, Y. So we're going to take here is node number 1, here node number 2 and here node number 3. So this one as member 1, this one as member 2. And for near far direction, from node 1 to node 2, so near far, this one is near far. Now we need to do numbering for unknown displacement and known displacement. For this type, we're gonna have X, Y and Z displacement. Z is rotational. So due to 20 kN, certainly we know at node 2 we'll have horizontal displacement. So that's 1, then vertical 2, and also gonna have rotational, that 3. Since 20 kN to the right, so there will be displacement which is horizontal at node 1. So that one is number 4. So those in red is unknown. So at nodes 1, we're not gonna have vertical displacement, which is 0, but for the rotational we're gonna have some value on that. So we need to do numbering for rotational first, so that 5, then followed by vertical displacement, that's number 6. Then go to nodes number 3, horizontal 7, 8, 9. So we done numbering between known and unknown displacement. Now we can calculate lambda x and lambda y for our member. First of all, we have to identify our origin. So we're going to take node 1 as 0, 0. That means nodes number 2 is 6, 0. And nodes number 3 is 6, negative 6. So from that, we can calculate lambda x and lambda y. So for member 1, lambda x is for x minus near x divided by L. So 6 minus 0 divide by 6. So 1, and for lambda y, please remember the formula. It's 0. So now let's calculate lambda x and lambda y for member 2. For lambda x, 6 minus 6 divide 6 is 0. And for lambda y, negative 6 minus 0 divided by 6, so negative 1. Also, previously, in the notes, lambda x also equal to cos theta, lambda y equal to sin theta. For member 1, so this new angle for that is 0 degree. So theta is 0. That means lambda x cos 0 is 1, sin theta sin 0 is 0. How about for member 2? For member 2, here, this near, this is your x direction, this is y direction. Angle for that is from here to there. So angle for that is 270. So find what is cos 270, what is sin 270. So this is another method to find lambda x and lambda y by using angle. But please be careful, you need to identify the direction of your angle correctly. If not, you will get wrong way. So the best way by using coordinate, so it's less mistake going to happen. Then we need to identify our matrix Q and D. From the constraint at 1 and 3, we know our D known, D6 to D9 is 0. So we need to find our matrix for Q. So this one for Q, this one for D. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So D1, D2, D3, D4, D5, 6, D7, D8, D9. Similarly for Q, Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, Q9. From the constraint, D6 to D9 is 0, so here is 0, 0, 0, 0. So we know the boundary between unknown and known is here. And here as well, between Q unknown and Q known. Back to the question, as we can see here, the 20 kilonewton force at node 2, and that's on direction 1 here. So Q1 for that one is 20. And no any external forces given for this question. That means Q2, Q3, Q4, Q5 is 0. So we assemble our matrix for Q and D. Next, we have to assemble our member stiffness matrix by using this formula for member stiffness matrix. As you can see here is nx near y near z, and this one is far x far y far z. Similarly on this side, nx and y and z, fx fy and fz. As what we had learned previously, this is symmetrical matrix, so it's enough for you to find half side, and the rest you just easily copy it. As you can see here, there's a pattern of the formula, so that means you don't need to calculate one by one. You can do by categorize it first. So let's do it. So we know our value for I is 180 times 10 power of 6 mm power of 4. Then our area is 6000 mm square. Then our E is 200 GPa. Be careful on converting your value between meter, kilometer or mm. For both members going to have same parameters, AE over L, 12EI power L3, 6EI, 4EI divided L, and then 2EI over L. So let's calculate for AE over L. So be careful with the unit given and the unit you want to. So this unit in kilonewton per meter. So convert it carefully. Next we're going to find 12 EI divided by L. Sorry, L power of 3. 2 kilonewton per meter. Next, 6 EI divided L power of 2. 6 times 200, 10 power of 6. Divide 6 power of 2. So 6 kilonewton meter. Next, we're going to find 4 EI divided by L. 4, 200, 10 power of 6. So once again, convert it carefully to the unit we want to. So this one, 24 times 10 power of 3 kilonewton meter. Next, we're going to find value for 2 EI over L. 200, 10 power of 6, 180 times 10 power of 96 divided by 6. So we get 12 times 10 power of 3 kilonewton per meter. For member 1, we know our lambda x is 1, lambda y is 0. So we can assemble member stiffness matrix K1. Then don't forget the numbering for member 1. x, y, z new, then x, y, z form. So for that numbering for member 1, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3. So it's enough to find half side. So we done half side. Then the next one, you just copy it easily. So we done for member 1. Next we're going to do for member 2. Lambda x is 0, lambda y is -1. So numbering for member 2, 1, 2, 3, 7, 8, and 9. Always x, y, and then z. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. So please find those values inside this matrix. 2, 0, -6, -2, 0, 6, 0, 24. Done half side and easily copy it. So, -6 and 0. So we assemble for member stiffness K1 and K2. That means our structure stiffness matrix size is 9 times 9. That for 2 member. Remember, if you have more member, you're gonna get bigger matrix size. That means for your work-based project, please try to do this example first in Excel, then later you can duplicate that to do it for your work-based project. Now we need to assemble our structure stiffness matrix, which is capital K. Q equal KD. So you need to assemble this capital K, which is this matrix. We already identified this line previously. Here, so you know the boundary between known and unknown for this one. Then find this one. One, two, three, four, 5. 1, 2, 3, 4, 5. So this is the boundary. So that means we identify what is our K11, K12, K21, and K22. Once you assemble this, you can solve and find unknown parameters such as displacement, forces, or reaction. By solving this, we get the answer. By solving QK equal to K11 du plus Ka12 dk, we get the displacement as you can see here. And then by solving QU, K21 d unknown plus K22 dk, we're gonna have forces or reaction for our system. That means you need to expand this matrix, solve the simultaneous equation by using matrix reduction or using your calculator, and you will get those unknown parameters. For this case, easily you can cancel out decay because decay is 0. So here is 0. Before I forget, for D1 and D5, the unit is in radian because it's rotational. So unit in radians. So from radian, you can change to angle. Alright, now we can determine the internal loading at joint 1 by using this equation. Q1 equal to stiffness K1 transpose matrix 1 times by D to get the internal loading at joint for member 1. Alright, for transpose matrix, we can get from this arrangement where here is D equal to TD, or transpose matrix is this matrix. So we need that matrix to be imposed in Q1 to get internal loading. So let's assemble this matrix. So we get in this form. This is matrix for member 1 with numbering 4, 6, 5, 1, 2, 3. Similarly, for D, here we already defined what is the value for unknown D. So the arrangement similar to numbering for K1, 4, 6, 5, 1, 2, 3. And then for transpose matrix T1, you need to find it out here. This is transpose matrix. And finally, by solving this matrix, we will get Q4, Q6, 5, Q1, Q2, and Q3. Once we get those Q4, 6, 5, 1, 2, and 3, let's draw those forces and moment on each member. So for member 1, you need to check back those numbering for X, Y, and Z. So as we got here, Q1 is 0, Q2 is 7.5, that means going up, and Q3 is negative 45. This is direction on member 1. So let's draw those forces and moment. Q1 is 0, that means no magnitude, and then we get Q2 7.5, that means going up because it's positive. So that's Q2 7.5 kilonewton. Then we have Q3 negative 45. Check back direction for 3, that is anti-clockwise for positive, but we get here is negative 45, so direction is this way with magnitude 45 kilonewton meter. So since at this end is going up, so at this end is going down with the same magnitude of 7.5 kilonewton. And then for Q5 is 0, Q4 also 0. Now let's do for member 2. Q1 is 0, Q2 is 7.5, but now that's on member 2. That means direction is again for member 1. So 7.5 kilonewton. That means at the other end, against the direction, 7.5 kilonewton. That means that in equilibrium. Now let's see for Q3 with the moment of 45 kilonewton. On member 1 is anti-clockwise. That means that direction need to be against that direction with the same magnitude. So in this direction is 45 kilonewton meter. On the other side, going to against that moment with the same magnitude. So 45 kilonewton meter. Also, there is external force in x direction with 20 kilonewton here. So at other end also 20 kilonewton. So once you done this exercise, my advice for you, try to do those metric calculation in Excel, because later on you're going to apply that for your work-based project. Right, thank you very much. Assalamualaikum and have a good day.